this weekend. That was kind of exciting. A grouse. Like a bird about the size of a chicken. I think it was a mother. Okay. So number 1 says, let R be the region bounded by y equals x squared, y equals 1, and the y-axis. So one of the big steps in this whole process is being able to recognize regions, because that's how everything we do, you start with a region and then you do something with it. What do you do with it? You could rotate it around the y-axis, you could rotate it around the x-axis, you could rotate around some other horizontal or vertical line. You can actually, and we haven't done this yet, but you can build like a 3D space, like you treat the region as a base and build something out on top of it. So that's the main 3 things. But all of them start with a region that's described in the XY plane. And so that's one skill. You need to be able to read this information and be able to picture the region. And you'll notice the way I did this is I picked one region and called it R, and then every problem on this sheet uses the same region. Okay? And that's for a specific reason, so that you can see how the region is related to and distinguish between what the region does and what the method of making the solid. Because when I describe a region, it's just a 2D space, right? And we turn it into a 3D space by doing something to that region. Okay, so part A says, find the area of the region. So this is not a 3D volume thing, this is just area, right? So let's begin by, before I do A, let's get the region. So what does R look like? So I'll draw a little XY plane here, and it says, the region bounded by y equals x squared. So y equals x squared looks something like, whoops, a daisy. Looks something like this. And then y equals 1, which would be right there. And the y-axis, which would be right here, of course. And that's it. So you can see here, we don't, instead of having 4 fences, we have, and I like to think of the equations as fences. So this, you describe this area by, so what's between, now in this case it's yeah, actually I guess that the y-axis divides it into 2 pieces, doesn't it? I should have said in here in the first quadrant, because what I was trying to describe was this little space right here. And grab a different color. Red. So we're talking about this space right here. Okay? There's a couple of sheets up here, if you want to grab them. Okay, so do you see the red kind of, other than John? Well, here, I'll just erase everything else. So that's the region we're talking about. Okay? So first of all, part A just says, find the area of that. Now that's something we did at the very beginning, right? To find area, you're going to divide it up into little rectangles and write an integral, right? And we're not talking Riemann sums here. We're just saying find the exact area. So you want integral, so you're going to go the integral from, and we could do this with dx or dy, right? Which one makes more sense? Dx, because I think it makes more sense to do a little rectangle like that. You see that? And so how do we know that's dx? Okay, I'm going to blow this up a little bit. I'm going to go over here. If we're going to draw it, I might as well draw it so you can see it. It looks something like that. Okay? And so if you draw a little rectangle like this, you can tell the thickness is running along the x-axis or parallel to the x-axis, right? So that would be a dx. So we'd put a little dx here. And that means we want to put our limits of integration in terms of x. So this is running from 0 to 1, right? Because when x is 1, y is 1. And we know that, or in other words, we know that point, stay here because you're recording. We know that this point right here is the point 1, 1, right? So we know the x coordinate is 1. So the limits go from 0 to 1. Now we just got to determine what's the height of the rectangle, because remember the dx is the width of the rectangle. So what is the height of the rectangle? Well, it's the top line minus this curvy line. The top line is 1. The curvy line is x squared. Okay? Any questions or comments about that? Notice there's no pi r squareds like we've been talking about because we're not finding volume right now. We're just finding area of the region, right? This is an old, like, first 3 weeks type problem. Okay, everyone cool with that? Any questions or comments? And then, of course, you could integrate that quite easily, hopefully, at this point. That would be x minus 1/3 x cubed, evaluated from 0 to 1. And that would be, what? Oh, the answer is 2/3. Yeah, so it'd be 1 minus 1/3, which is 2/3. Okay? Everyone happy with that? Nothing crazy or spicy there? Okay, we go to part B. It says, find the volume of the solid. So this is where, again, like I said, we're going to be rotating R. Everything has an R in it. So we're taking that region and we're doing something different to it each time. And it's going to create a completely different solid. Okay? So this one says, find the volume of the solid obtained by rotating R around the y-axis. So let's draw another picture. So if we rotate it around the y-axis, that means we're going to get something that, if we do a cross-sectional area, it'll look kind of like that, right? And if we try to give it some 3D, gives it a little bit of 3D, right? So it looks like again, the tip of a bullet, sort of. Okay? So, is this disk? Are we adding up disks? Adding up donuts, as I think someone said on Thursday. Disks. How do we know they're adding up disks and not washers? There's no hole in the middle. So let's talk about in general, how do we know before we even drew the picture? Because some of us are not very good at drawing the pictures, and I include myself in that. How would we know, what's a general way of telling whether we're going to have to use washer or disk? Yes. Good. So, or another way to say that is if the line of rotation is on the border of our region. Does that make sense? Notice that the y-axis is one of our boundaries, right? So that means if I'm rotating around something that touches my region, then there's not going to be any hole in the middle because everything is it's brushed up against it. Now, if only part of it was touching, then that would create a little hole. Like the part that's touching there wouldn't be a hole. But sometimes you have this where you have something that looks like this maybe, where it comes up like that or something. So then there'd be a hole in that part up here, right? But there wouldn't be down there. So you'd have like a little bit of an indentation. So it's if the region is completely touching, all the way along the region is touching the line of rotation, then you won't have a hole. It'll be a disk. If it's not touching at all or not touching the parts, then there'll be a hole and we'll have to use washers. Okay? Does that make sense? Awesome. So if we're using a disk, then we know that we're just doing this, right? Pi r squared. We're adding up a bunch of short cylinders. And I like to say short cylinders because that reminds me that this is actually pi r squared dx, right? Or d something, I guess I should say in this case. D something. Now this is where the visualization comes in. If you're a good drawer, that helps. But there's a picture of the top disk, right? Does that help you determine whether it's dy or dx? Which is it? dy, because the little short height of the cylinder is running parallel to the y-axis, right? So it's got to be dy. Okay, so we're going to put a little dy in there in place of h, and now we're ready to go after it. Once we determine that it's dy, then I can start building the integral. So that means that limits of integration are going to go from, we're going to look at y values, right? So what's the lowest y value? 0. And what's the highest y value? 1. Good. We have a little dy out here. Now we just have to come up, and we can put a pi right there. We can put it inside or outside, whatever you feel comfortable with. Then all we need in here is an r, and we'll put the little squared in already. Okay, we just need to find an r and square it. So now this is sometimes the difficult part. What is the r? Now it's helpful to draw an r. In fact, I've already drawn it, but I'm going to erase that so it doesn't look confusing. There's my r right there, that little red line. That's the r, right? Here's another one down here. Here's another one down there. So we can tell that the r is changing, right? I think that's an important question. Ask yourself, is the r changing or is it the same all the time? In this case, it is changing, right? As we go from the bottom to the top, it's getting bigger, isn't it? You see that? What's determining how long the r is? That little x squared line, right? The y equals x squared. Now, so that would be easy. I could just put an x squared in here, but then I stop and say, well, I can't put an x squared in there because it's dy, so I have to have in terms of y, don't I? I can't have an equation with x in it with a dy at the end. It doesn't work. So I have to take, but I do know that the radius is determined by this equation, right? So all I have to do is take that equation and adjust it so it's in terms of y instead of x. How do I do that? I just solve for y. How do I solve for y? How do I solve for y? Solve for x. So in terms of y. Yeah, I just square root both sides. So I have the square root of y equals x. So that means I'm going to go back up to there and say, oh, my radius is just the square root of y. Now, I also want to make sure you understand something. That notice that if we pick this point anywhere along here, right? The point where the radius touches that line, the end point of the radius, let's say, is always, see if this makes sense to you, always x comma x squared. Do you buy that? That's the coordinates of that point. But it's also always square root of y comma y. Do you buy that also? And this is really important to understand, especially when you get to the shell method. To be able to look at a point and be able to say it in terms of either y or x. So if you pick any point on that line, you could say it as the square root of y comma y or x comma x squared. And that's what we're doing when we switch back and forth between x and y. Being able to determine one coordinate in terms of the other, depending on which one we want. Often the equation is given to us with y in terms of x. So usually if we want x in terms of y, we have to undo it. But you should be able to go both ways. Now, as I warned you, the hardest part about these is setting them up. Usually we end up with a fairly nice integral, and this is absolutely true in this case because we have a pi on the outside, a 0 to 1 here, and of course the square root of y squared is just y dy. You can't get a much harder integral than that. Easier, sorry. And so this is going to be equal to pi halves y squared, value from 0 to 1. Plug in a 1 in there, and we get pi over 2. Is everyone happy so far? Not that your happiness is solely dependent upon your ability to integrate. Okay. Part C, find the volume of the solid obtained by, okay, we're doing something with R again, rotating R. We're still rotating. Now we're going to rotate around the x-axis. Now this will make a completely different shape. Yeah, we're going to get a little hole, aren't we? Okay, so there's the region, same region as before, right? Let me draw a cross-sectional area. Looks something like that, right? So this looks like a, what does it look like? It's got a cylinder on the outside. If you just looked at it from here, it looked like just plain old cylinder, but then you go up on top and there's a little kind of a, indentation going in like this, sort of. Almost like a funnel, sort of. Except for the sides that kind of, I guess funnels do that. They kind of curve in, don't they? Yeah. Okay? Everyone see it? So, we're going to stack up some things to create this. Are we stacking washers or are we stacking discs? Washers, because now there's a hole. Because once again, if we go back to what we said before, notice the line. This edge of the region is not touching the line of rotation except for at the very end there, right? And so that warned us, when we noticed that at the beginning, that warned us that there's going to be a hole when we rotate this. So we're going to have to use washers, or donuts, as some of you are keen to say. Come on, dude. Go back to green, pin. Good. Okay. So now, I think these are the trickiest. Because it's a washer, we know it's going to be pi on the outside. We're going to integrate something, and we're going to have something squared minus something squared. Yeah? And it's going to be, is it going to be dx or dy? Dx. Excellent. How do we know it's dx? Because if we try to draw a little washer here, you can see that the thickness is running parallel to the x-axis. Can you kind of see that? Does that help or hinder? So in terms of x, we're going to integrate from 0 to 1. Now you'll notice as we go along that these limits of integration will never change, because it doesn't matter whether they're going in terms of y or x, that it's the same, isn't it? And that's important. That's one of the reasons I did this, because the limits, and I said this on Thursday, the limits of integration are completely determined by the region. Whether you rotate or around the x or y, or whether you do other things we're going to do, has no effect on the limits of integration. The limits of integration is completely determined by the region that I'm working with. Okay? So you don't let all the other stuff confuse you. Okay. So now we just got to come up with our r's. And this is where, again, as I said before, I think it's helpful to draw some sample r's. So let's start with the big R. And again, I think it's also very helpful to ask yourself, is the big R changing? So where is the big R? The big R goes from the line of rotation to the outside edge. Right? So is that line changing? As I draw a line anywhere along this region, from the line of rotation to the outside edge, is it always the same or is it changing? It's always the same, because that outside edge is a straight line, isn't it? Okay? So what is the distance from the line of rotation to the outside edge? 1. So my big R is just 1. Isn't that nice? Then we go to the small r and we ask the question again. Where's the small r? It's from the line of rotation to the inside edge, or you could say the edge of the hole, if you will, if that makes more sense. Now, is that changing? Is the hole getting bigger or smaller as we go from left to right? Yeah, it's getting bigger, isn't it? And what's determining the length of the inside r? That same line, isn't it? And that's in terms of x, is x squared, so I'm just going to throw a little x squared in there. Isn't that slick? So now we have a pi integral from 0 to 1 of 1 squared is just 1, and x squared is x to the 4th, and we have a dx there. So if we integrate that thing, we're going to get pi x minus pi over 5 x to the 5th, and we're integrating from 0 to 1. And of course, that just gives me a pi out front and a minus pi fifths, and that equals what? 4 pi over 5. Okay, I'm going to keep rolling. If you have questions, please stop me at any moment. So far, we really haven't done anything new from Thursday, right? This is kind of the same stuff we were talking about on Thursday. We mentioned that it can go in the y direction or the x direction. Haven't got anything crazy yet. Number 6, or number D says, find the volume of the solid obtained by rotating R. So they all start out the same so far, right? So let's draw the R again. Find the volume of the solid obtained by rotating R around the line. Oh, now this gets interesting. X equals -2. Dun, 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 dun. There's my line of rotation. So everything is rotating around that line, which means it's going to stay the same distance from that line, right? What did I say? Oh, x equals -2. Oh, that's even more interesting. Thank you. Actually, it's not more interesting. It's equally interesting. Thank you for catching that. So, again, as I was saying, when you're rotating around a line, that means everything stays the same distance from that line, right? So this edge that sits on the y-axis is now going to be right there. See that? When it rotates around to the other side. And it's from there, it's going to go over about that far, and it's going to come down like this. So again, I think it's helpful to draw a cross-sectional because you can kind of see. And then if you're able to do it without confusing yourself, you could draw in the inner circle, right? And the outer circle. That gives you an idea of what you're dealing with. I think that helps you see whether it's washer or disc. But once again, if you know that it's going to be washer because the line of rotation is not touching the region, right? Okay, so we know it's a washer. Once again, I'm going to integrate from 0 to 1 because the region hasn't changed. And is this going to be a dy or dx? It's going to be a dy. Everyone agree with that? You see why? Why? Because the little thickness is right there. Okay? And since it's a washer, we got to come up with a big R and a little r, and we're going to square them both, and we're going to put a pi out there. Start with the big R. Is the outside edge changing or staying the same? It's changing. So the distance from the line of rotation to the outside edge is changing. So and it has to do with x squared, but it's not exactly x squared. But I got to change that to square root of y because we're dealing with y's, right? So this line right here, this line we're going to refer to as x equals the square root of y because we want it in terms of y, right? But the actual radius is like that. That red line. Do you see it? So now, the part that's part red and part green is the square root of y, isn't it? Do you see that? And then, so we got to come up with the part that's just red, or just has one line, and that part is always 2, isn't it? Now this is where this is where people have trouble because they think, well, how is it 2 if the line of rotation is -2? I'm confused. Because remember, you're just looking at distance. How far is it away? So this distance right here, no matter where I draw it, is always 2, isn't it? Right? Every one of those red lines is 2. And then the rest of the radius, when you add it on, I'll grab a different color so you can see it. I'll try to grab a different color so you can see it. There we go, blue. Notice the blue line is changing length, isn't it? And that blue line is always just the square root of x, or square root of y, sorry. So, in the end, we know that it's 2 plus the square root of y. Okay, I think this is the first one that's a little bit kind of challenging. So we all okay with that? Any questions about that? You see where those numbers and letters are coming from? And then we get the little r. Well, the little r is all those little red lines that I drew, isn't it? Everyone see that? The little r is not changing because that inside circle is just a nice cylinder. It's just the same all the time. And so that's just going to be 2. Okay, so this one now forces us to do a little algebra. Woo! We got to square that thing, so that's going to be 4 plus 4 times the square root of y plus y minus 4. All the thing dy. And of course the 4's will cancel out. That's kind of nifty. And we get 4y to the 1/2 power just to set it up to get ready to integrate. And there's a y there. Then all that's times dy. And we get pi times, let's see, y to the 3/2 power. And so that would have to be 8 over 3 to get a 4 out there. And that would be 1/2 y squared. And all that's evaluated from 0 to 1. Plug in 1, and we get 8 pi over 3 plus 1 pi over 2, and then 0, 0. So that's going to be what? 16 plus 3 is 19 pi over 6. Bless you. Questions or comments or concerns? Okay. All seems pretty peaceful so far. Find the volume of the solid obtained by rotating r around the line x equals 3. Again, notice how different each one of these shapes are once we rotate them. Rotating the same region, but it's ended up looking very different each time. So you can draw a lot of things with this. Find the volume of solid around the line x equals 3. This is kind of interesting. So you can see it looks kind of like this. Yeah? Okay, I'm not going to draw the disk this time and see if we can just do it from looking at the radii, because I think some of you will probably want to do it this way, because drawing the disk will just, depends on whether you're a good disk drawer or not. It might confuse you. So we'll start off with what we already know. We know it's got to be from 0 to 1. And are the discs being stacked up, or are they being run along a line, which means is it dy or dx? Dy. It's got to be dy. Is there a hole in the middle or no? Yeah, so it's got to be a washer. So that means we're going to need a something squared minus a something else squared. And we'll throw pi outside. Okay? Now, what's the big R? Is it changing or the same? The same. That outside edge is just a straight vertical line, isn't it? So it's just the same all the time. How big is it? 3. Just straightforward 3, isn't it? You can just count it out no matter where you go, up and down. The distance from the y-axis to the dotted line is 3, right? So you put a little 3 in there. How about the inside edge? Oh, now this is a tough one. I think this is the toughest one to see. So the key to understand is that this distance right here is, as we've said many times, is the square root of y, isn't it? Right? And what we want is, here I'll do highlighting so you can see it. What we want is this line right there. I'm sorry. No, that's not right. What we want is that line right there. Right? And also, what we know is, I know some of you already have this figured out, but I'm taking my time to make sure we all get it. We also know this green line is 3, don't we? So we have 3 links there. We have the whole thing, that basically it's the big R is 3. That's the green line. And that green line is made up of the dark green and the yellow, right? So the dark green, we know is the square root of y. And the yellow, I don't know what that thing is. Right? So I can't really add the square root of y to something because that thing's changing all the time. So what makes more sense is to take the square root of y that's changing, and I have a phrase for that, and just to subtract it from the highlighted green. Does that make sense? So this thing is 3. This thing is going to be, oh, shoot, I got to get my color back here. Sorry. Pause. This is going to be 3 minus the square root of y. Because I'm taking that total distance between the y-axis and that dotted line, which is 3, and I'm subtracting from it the distance from the y-axis to my function. And that leaves that little snippet in there, which is the small radius, or the small r. Okay? Now, once again, this is not one of those things where you can come up with the algorithm and say, every time the line of rotation is here, we do this. Every time the line is rotation here, we do that. You really have to draw the line of rotation, draw your region, and look at it and figure out how to determine the radius. And sometimes it's a number plus something. Sometimes it's a number minus something. Sometimes it's a function minus the number. I mean, it varies from situation to situation. Yeah. Question. Well, because yeah, you're kind of asking me to do what I just said you can't do, but I'm going to try to do it anyway. Once again, the problem is you can't come up with a general statement that describes everything that's going to happen. You kind of have to look at each individual case. But the difference between this one and that one, which is a good question to ask, notice that the square root of y is okay. In this one, there's a set number we know, which is 2, right? Here, there's also a set number that we know, which is 3. Okay, that's the similarities between the two. The difference is that this one is going to be the set number, and then you go beyond that to get to the other side, to get to the outside edge, right? Here, the square root of y is inside that set number of 3. You see that? So the set number 3 that we know contains the other thing we know, the square root of y. Here, the thing we know, the square root of y, and the set number 2 are just sitting beside each other. They're not inside each other. And that's the big difference between the two. I don't know if that helps, but that's why this one is you're adding the two, and this one you're subtracting one from the other. Does that help at all? Yeah. Because in both cases, we know 2 things, and we don't know the third thing, right? So we have to come up with a expression for it. And here, you just look at it and go, well, the thing I know is bigger than the thing I want. Or the 2 things I know are, you have to subtract one from the other to get the thing I want. Here, you got to add the 2 things together to get the thing I want. That's why I say it comes back to just kind of logic. You're looking at your little line. And I think it's helpful to get some colored pencils, honestly, and draw the 2 things I know, and then the other line that I really want, and say, is it this plus this, or is it this minus this? And if you have colored pencils or a pen and pencil or whatever, it'll help you see the 2 pieces or the 3 pieces and see how they come together. Okay? Okay. So then, of course, we can finish this by going pi, and that's going to be the integral from 0 to 1 of 9 minus 6 rad y plus y dy. And of course 9 minus 9 is 0, but that's going to turn that into a positive 6 times the square root of y and a negative y. All that's dy. Did a little bit of algebra, but now we're ready to integrate. So we're going to have a pi times, let's see, that would be 12y, nope, that'd be y to the 3/2 power. And we want that to be, what, 2/3 times 6 would be 12/3 would be 4. Minus 1/2 y squared. Yeah, that works. So then when we plug in 1, we get 4 pi minus pi over 2, which is 8 pi, that'd be 7 pi over 2. How are we doing? Is it all digesting okay? No one's getting a sour stomach yet? Or a sour brain? I wonder what that would look like if your brain threw up. Find the volume of a solid obtained by rotating r around the line y equals -2. That's what I was going to do earlier when I was stopped. There's y equals -2. There's my region. There's my crooked line. Let me draw it straighter. Your ability to see things definitely gets better the more of these you do. Yeah.
For the last problem, did you also, instead of doing a root y, 3 minus root y, the second part, you also use y squared plus 2?
Y squared? You mean x squared?
Y squared, x squared, yeah.
I don't see that.
Instead of like using the whatever shape they created, using the x squared underneath x squared plus 2. get that inner area. So then you have 9 pi minus the inner area.
If you're using x squared, then you're stacking things like this. I'm sorry, you're stacking things like this, right? And I don't see how you can get that inner area by stacking like this.
Well, we use the from 0 to 1 of x squared and plus the center cylinder we use 2. And that would give you the inner area, right?
Can you walk up to the screen and show me where the plus 2 is?
Yeah.
So we got 9 minus x to the 4th. Let me just distribute the negatives as I go this time. Minus 4x. I said x to the 4th, but wrote squared. Sorry about that. X to the 4th. 4x squared minus 4. All that dx. And it looks like the 9 minus the 4 is going to give me a 5. Oh, shoot, it didn't disappear this time. So that's going to be a negative x to the 4th. Minus 4x squared plus 5 times dx. Then when we integrate that, we get negative pi over 5 x to the 5th minus 4 pi over 3 x to the 3rd plus 5x, evaluated from 0 to 1. So then we get negative pi over 5 minus 4 pi over 3 plus, whoops, I left out the pi in that one, didn't I? Sorry about that, 5 pi there, plus 5 pi. So we have negative 3 pi over 15 minus 20 pi over 15 plus 75 pi over 15. So that would be negative 23 and 75. So that would be what? 52 pi over 15?
That's the answer that I got when I did my last problem.
Oh, really? Nice. Yeah. So let's go to G. We're going to make it through this? Not really. Okay. I'm going to skip down too because I think we're getting this rotation thing down to do I. Because it's completely, and now for something completely and totally different. Find the volume of the solid with R as the base. Oh, so we're not rotating anymore. Dun, 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 dun. Find the volume of the solid with R as the base and cross-sectional areas of a semicircle. So that means you've got a base. So here's like the footprint of a house, right? And then we're building up from that base, just semicircles. But the diameter of the semicircle is determined by how wide the base is. Find the volume solid with R as a base and cross-sectional areas of a semicircle. Okay? I didn't say which way the semicircles are running. Let's say that the semicircles are parallel to the y-axis. Okay? Add that in there in your notes. So that means what is going to happen is I'm going to draw a little semicircle that has a little bit of thickness, and it's going to come out like this. You kind of see that? Does it help if I make it bigger? So notice that that semicircle as you go from left to right, is going to get smaller. Okay? So it's going to be real tall at the beginning, and it's going to kind of come down like this. Okay, so the circle will get smaller and smaller and smaller as it goes to the right. Everyone see that? So once again, this is why we spent some time with Raymond Selms right before we got into this, because remember the integration is just adding up a bunch of things. So when we look at this, what is it that we're adding up? A bunch of semicircles. That's all we're doing. It's fine. Adding up a bunch of semicircles. Well, really, they're semi-cylinders, aren't they? Because they have a little bit of thickness. A circle with a little bit of thickness is a cylinder, right? So this is a semi-cylinder, which is not really a term, but you understand what I'm saying. It's a half of a cylinder, right? And once again, the thickness or the height of that cylinder is what? In terms of the integration? dx. Everyone see it? The thickness of the cylinder, or the semi-cylinder, is dx. Okay? So when I go to write an integral for this, let me shrink it back down. It's going to be, again, from 0 to 1, because the region hasn't changed. It's still the same exact region, from 0 to 1. It's going to be dx, because that's where the little infinitesimally small thickness is. And now we just have to come up with the formula for a semicircle. Well, the formula for a semicircle is just half pi r squared. Do you buy that? Because a circle is pi r squared, so a semicircle would be half pi r squared. Just cut it in half. And now, this is the tricky part, we have to come up with the radius. Now, the easy part is that the radius is just half the diameter, and the diameter is a lot easier to see here, isn't it? What's the diameter of that semicircle no matter where I draw it? 1 minus x squared. Okay, so again, here's x squared. We'll make it squiggly just like we did last time, right? And the thing I'm looking for is right here. Right? The thing I'm looking for is a straight line. Let me blow that back up. And the x squared is this squiggly line, isn't it? So how can I get that straight line? I know the top, the whole thing, those two added together is 1, right? Because it stops at the top. So if you take 1 and subtract off the squiggly, you get the diameter. So in here, I'm going to say 1 minus x squared. But of course, I'm looking for a radius, so I have to cut that in 2, don't I? So I put a little 2 there. So 1 minus x squared is the diameter. I divide that by 2 to get the radius, because the radius is what I want. The radius is what I want to square. We okay? Okay, just because we're running out of time here. What if, I'm going to change this up on you real quick. What if, because you guys can do that integral there. What if instead of semicircles, same region, I'm going to draw squares. Okay? So that means, hold still here, buddy. That means I'm going to have a little bloomp, and I'm going to have something coming out of this. Ah, man, this is going to be trouble. I don't know if that's helping any. But the key here is, what is it that I'm adding up? Not semicircles anymore. What am I adding up now? Squares with a little bit of thickness, so that makes them prisms, right? Or boxes, or whatever you're going to call them, right? But it's a square base and has a little bit of thickness. What is the little bit of thickness again? It's the same, isn't it? It's still just dx, right? So over here, I'm going to have the integral from 0 to 1. I'm going to have a dx out here, and I'm just putting the formula of that square. what is a square? A square is just length times length, right? Or side times side. What is the length of the side of that square? It's the same as the diameter of the semicircle, isn't it? Yeah, so I just put a 1 minus x squared in there, and I'm going to square that because it's length times length, right? Or side times side. I have one side on the base, and then the other side sticking up like this. Okay? Yeah. Right. That's why there's no fire thing. I'm just saying the base we're not doing is fine.